In this video, we'll go over the second half of the Training Models and Ensembling notebook. Here we'll cover topics like stack ensembling, bagging, and the pros and cons of ensembling versus hyperparameter optimization. Recall that in our weighted ensemble, we simply combined individuals' models' predictions via a simple weighted linear combination. However, why should this be the optimal method of combining predictions? In stacking, one instead trains another stacker model that takes in the predictions of the individual base models and learns how they should be best combined. This can be achieved by simply training this so-called stacker model on a newly constructed data set where the features are now all of the base model's predictions, say, concatenated together and using predicted class probabilities for classification tasks, and the target values in this data set would remain the same as in the original prediction task. The stacker model can thus rectify shortcomings of the individual base model predictions and exploit interactions between the base model predictions that offer enhanced predictive power. But how do we know what kind of model the stacker should be? Since we don't know, we can just train multiple types of stacker models, just like AutoGluon originally trained multiple types of base models on the original data features. We can once again aggregate these stacker models' predictions via yet another weighted ensemble, or alternatively, we could aggregate them via yet another stacker model. The idea of feeding the predictions output by stacker models as inputs to higher layer additional stacker models is what we call multi-layer stack ensembling. This has been a prominent prediction strategy in very famous competitions like the Netflix prize, for which the winning team won $1 million with multi-layer stacking, and Kaggle's auto product classification challenge. In this multi-layer stacking strategy, one often still will use a simple weighted ensemble at the topmost layer of the stack. The form of multi-layer stacking used in AutoGluon is shown below, here for 2 layers of stacking and n types of individual base models. Here, the input to each model at the base layer is just the original data features, denoted as input below. Each model then produces predictions, which we concatenate together into another feature vector. Then we actually concatenate the original data features with the predictions of the base models, and that is the input for each of the stacker models in the first layer. Subsequently, we apply a weighted ensemble to aggregate the predictions of these second layer stacker models, and that's how we get our final output prediction. Stack ensembling is one technique that you can specify to boost accuracy in AutoGluon. However, its efficacy is limited without another technique that we'll introduce here. To see why, first let's understand that during training in FIT, stacker models must only operate on predictions from base models for data points that were held out during the base model's training. If a stacker model were to be trained on a prediction from a base model on a data point that the base model saw during training, the base model could be overfit to that data point's label, for example, memorizing its label, and thus leading the stacker model to believe that this base model is highly accurate. If we use a standard training validation split, that means we can only use the validation data to train our stacker model. This strategy is known as blending, but it obviously does not generalize to the multi-layer setting, where each additional stacker layer would have less and less data to work with. Instead, in AutoGluon, we use bagging to train stackers only on data held out from lower layer models, while still being able to learn higher layer models over the full data set. Bagging, or Bootstrap aggregation, was popularized by Leo Breiman, and the idea goes as follows. In k-fold bagging, we randomly partition the data into k chunks that are disjoint, and we train k different copies of a model with a different data chunk held out from each copy. So here we're showing, for example, k equals 5-fold bagging. We have the original full data set here with all the rows shown here. Maybe In the first fold, we use the last 80% of the data as our training set and hold out the first 20%. Then in the second fold, we might use the first 20% plus the last 60% of the data set as our training set, holding the second 20% out as our validation set, and so on. Thus, we see that every single row in the data set lies in the validation set of one of these folds. That means it was held out from the models that were trained in that fold. With stacking specified, AutoGluon will automatically bag all models. Each model will produce out-of-folds predictions on the chunk of data that was emitted during its training. As just shown graphically, every single data point is out of folds for one of the copies in a bagged ensemble. So we always can produce out-of-fold predictions for every single data point from every single type of model. So just to recap, in the case of 5-fold bagging, for every one of the 5 training validation splits shown above, we would train one neural network for each of the splits, one cat-boost model for each of the splits, and so on. So in total, there would be 5 neural networks, 5 cat-boost models, etc. We call these 5 differently trained copies of the same model type a model bag or bagged ensemble. For example, the neural network bagged ensemble would actually contain 5 individual neural network models. At inference time, new data points count as out of folds for every model in a k-fold bagged ensemble, because presumably these points haven't been seen during training. For a test data point like this, we simply average the predictions of each model in the bag and feed the resulting output into higher layer stacker models. However, there's a subtle train test mismatch now, as the input features to stacker models are slightly noisier during training than during inference. This is because during training, stacker inputs are predictions from just a single model in the bag, whereas during inference, stacker inputs are predictions averaged across all models in the bag. To mitigate this mismatch, we'd like to do some sort of averaging of predictions during training as well. AutoGluon uses repeated k-fold bagging, in which multiple randomly chosen sets of k-fold data partitions and model bags are maintained. With repeated bagging of multiple k-fold bags, each data point remains out of folds for one model in each k-fold bag, meaning we can average the predictions over the multiple models for which this data point is out of folds, even during training. Thus, we are able to average some predictions during training, as well as averaging predictions during inference, which makes this mismatch less severe. Furthermore, just by having more bags in total, we reduce overall variance in the learning process. If you specify that AutoGluon should use multi-layer stacking during fit, its overall training strategy will look like this. Here, N denotes the number of bagging repeats, and L denotes the number of stacking layers, where each repeat of bagging involves splitting the data into k folds and training k bagged copies of models. First, we iterate over stacking layers. Then we iterate over the number of repeated bags. Within each one of these repeats, we just randomly partition the data into k disjoint chunks. Within each partition, we have a training and validation set here, and we train each type of model on the training set. Then we use that type of model to make predictions on the validation set, aka the out-of-folds data for that model. Then, after we've done this over all of the different train val splits in the k-fold bag, we average the out-of-folds prediction across the repeated bags for every type of model. And then we concatenate these averaged predictions together and concatenate them with the original data features, and that becomes the data features that are then fed back into the next stacking layer. Note that in step 6 here, if we don't have enough time to train all the types of models, that's totally fine. We can just train some types of models depending on what the time limit is. If a particular type of model fails for some reason while we're training it, that's fine too. We just skip over that kind of model and we just start training the next model type. To divide a given time budget between the stack layers, we just divide it equally so that each stack layer has equal time for training all of its models. To decide on n in practice, the number of bagging repeats, we typically will just complete one round of k-fold bagging and then see how many repeats of this can we actually complete within the user-specified training budget. Finally, to actually produce predictions or to obtain a validation score during training, the final set of the averaged out-of-folds predictions are combined via a weighted ensemble with weights chosen via the previously discussed ensemble selection method. So to actually maximize predictive accuracy on your tabular datasets, we recommend you run AutoGluon with automated multi-layer stacking like this. The only change here is that we've specified this auto stack argument, and it will automatically choose the right number of stacking layers and number of bagging folds and repeats for your data. Well, the repeats will just be chosen based on however much time you've specified. So let's see what happened during fit, noting that here we called it with an intermediate verbosity value to print out some more information during training. Again, the pre-processing part of the fit looks similar to before. There hasn't been any change with stacking. Now we're still training models as before, starting with the random forest. The difference to note here is that now the name stacker is appended to each model along with which layer of the stack it is part of. The base models that are just trained on the original data features are layer 0 models. And so here we start training these models and so on and so forth. And here we can actually see one of the models for which we start printing intermediate outputs during its training process, the gradient boosting model, the light GBM model in particular. And here we see the difference is we're not just training one light GBM model, we're actually training multiple light GBM models, even at the 0th stack layer, because we're using 10 folds of bagging here. So here's the first training run of a light GBM model. Then we have the second fold of bagging with a different training validation set here. Then the third fold, fourth fold, fifth fold, sixth fold, seventh fold, eighth fold, ninth fold, 10th fold. And then we're done and we save the entire bagged ensemble of all 10 of these light GBM models before moving on to the next model, say cat boost model. And then again, we train 10 bagged copies of this cat boost model and so on and so forth. And here we start training the neural network model, again printing out its architecture before training, and we start training the first epoch. But we noticed that we ran out of time because we didn't actually specify that much training time in the overall budget. And so actually AutoGluon just decides we're going to skip this neural net model because there's not going to be enough time to train it fully, especially with bagging, and it will just stop and go on to the next model if there were a next model. In this case, that was the last model, and so we're done, and in this case, there's no bagging repeats done because there just simply was not enough training time specified in the budget. If you increase the budget significantly, you'll see that it'll complete up to 20 k-fold bagging repeats, and it will be able to train the neural network as part of that. So that's the L0 models, and AutoGluon will try creating an ensemble out of the L0 models and evaluating its performance. Then it moves on to layer 1 stacking. So now we start training the same set of models again, but this time each of these models is operating on the predictions of the L0 models concatenated together with the original data features. So here we start again with a random forest model. Again, it's denoted as a stacker, and here you see it has the suffix L1, indicating it's a stacker model that operates upon the predictions of other models. And so we train that model, we start training extra trees models as before, now as L1 stackers, k nearest neighbors models, just as before as L1 stackers. And so what we do in this L1 stacker layer is we train every single model type just as before on the original data, but now on an augmented data essentially. And we use the same hyperparameter values for each one of these models as we did when they were base models. And skipping ahead, finally we create yet another weighted ensemble that here now tries to aggregate the predictions of layer 1 stacker models. And this is essentially our layer 2 stacker model, this weighted linear combination of the layer 1 model's predictions. And that's presumably going to be the thing that performed best on the validation data and the thing AutoGluon would use to predict on new data with. And so with AutoStack specified, as we just did, AutoGluon automatically will select appropriate values of k, the number of bagging folds within one repeat of bagging, n, the number of bagging repeats, which is just based on how much training time was specified, up to 20, beyond 20, sort of the benefits are very marginal, and L, the number of layers in the stack, which is typically 2. Here we inspect the test accuracy of each bag model at the various stack layers, again using this leaderboard function. So here you see the leaderboards look similarly to as before, just noting that each one of these models here is actually a bagged ensemble. Note that predicting with any L1 model from the second stack ensemble layer requires first computing predictions from all L0 models. Let's take a closer look at an L1 model. Here we load an L1 model, the random forest, from noting that its suffix includes L1, indicating it's a second layer stacker. And we can call the getInfo method, as we've done before, to see some information about this model. Here we notice that this model depends on 10 children models. Those are the actual random forest models, single random forest models, I should say, that comprise the bagged ensemble that this model is comprised of. Also, we can see the base model names. These are the models whose predictions this model relies on as features. So again, a stacker ensemble model object actually contains 10 different individual models within its bag when we're using 10-fold bagging, and possibly more if we're using repeated bagging. Here's what the actual data that gets fed into this model looks like. We can see this by calling the transform features method that will return the copy of the data used to train a particular model. Here we see that the data looks like this. We have the predicted probabilities of each class from each L0 base model. Here from the random forest classifier with Gini splits, here from the random forest classifier with entropy criterion splits, here from the extremely randomized trees classifier, etc., etc. But also these predictions are concatenated with the original features from the diabetes data set here. So what about hyperparameter tuning, you might ask? So actually, if you look at what people do in competitive data science, say in Kaggle, a lot of those data scientists spend more time on model ensembling with stacking and bagging than hyperparameter optimization, especially because they have strict training time constraints. They want to try out lots of different versions of their data rather than spending time tweaking hyperparameters. One issue with hyperparameter optimization is it often expends significant compute evaluating poor hyperparameter configurations that no reasonable data scientist would consider. Another issue is that if hyperparameter optimization is run for too long, it can start overfitting the validation set. This is counterintuitive because you would expect a good AutoML system would just keep getting better and better the longer it's run for. However, if you allow hyperparameter optimization to tweak too many hyperparameters based on validation data, it can really start to over-optimize. In contrast, stacking, bagging, and just model ensembling in general much more reliably keeps improving performance with additional fit time. That said, the accuracy of AutoGluon's tabular prediction module can still often be further improved through hyperparameter tuning, which you can easily specify via the hyperparameter tune argument of fit. Here we show a hyperparameter tuning example that only trains and tunes light GBM models during fit, and with some custom hyperparameter search spaces thrown in for fun. Here we specify some non-default search spaces that AutoGLON should consider in its hyperparameter search. AutoGLON will not only search over these, but will also search over other hyperparameters as it uses a default search space for every model. For example, here we specify that the number of leaves of each tree might be considered as an integer, searched between lower and upper bounds of 26 and 66. The learning rate used during gradient boosting might be considered a real valued hyperparameter that lies between 0.01 and 0.5, and it might be searched on a log scale with a particular default value to use first. And the type of boosting used during training might be a categorical hyperparameter with two possible options. And then we just call fit once again in the same way as before, this time specifying hyperparameter tune and passing in hyperparameters. And because the key in hyperparameters here is GBM, AutoGLON will only train a light GBM model and won't train any other models. And so we just run hyperparameter tuning here, and you can see that it will start running and training many models. And finally, we also still apply ensemble selection since it's so cheap to create a weighted ensemble of different light GBM models now under different hyperparameter configurations. After fit completes, we can examine the performance of all the models trained under different hyperparameter configurations during the HPO process. This can be done using the fit summary method applied to our train predictor. Here we show the performance of each light GBM model from different trials, where a trial corresponds to a training job that produced a particular light GBM model under certain hyperparameter values. We can also see the best performance achieved after a certain number of completed trials, where recall performance here always is with respect to the validation data. Finally, this fit summary method also produces a couple plots we can look at. This plot shows the HPO results from all the different light GBM models under all the different hyperparameter configurations. Here on the x-axis will be shown one particular hyperparameter. In this case, it happens to show the boosting type hyperparameter, which recall there was only two choices for. And on the y-axis, we show the validation performance, and you can mouse over any model here and see what hyperparameters were used to train that corresponding light GBM model. Here you can see it's not really clear that one type of boosting or another is actually noticeably better for this data. We caution here that the displayed performance numbers are internal metrics produced from the light GBM library, which are actually error rates that have their sign flipped because AutoGLON always assumes internally that higher values of these metrics are better. The other plot produced by fit summary summarizes every type of model produced during fit. In this case, we only trained light GBM models, so it's not too exciting, but here you can see also the performance on the validation data of the weighted ensemble. In this case, you can also see that the weighted ensemble itself has some hyperparameters. For example, max models and max models per type, which indicate it will only consider at most 5 light GBM models in the weighted ensemble, and at most 25 models in total will receive non-zero weights by the weighted ensemble. Finally, we recommend you check out these references to learn more. These cover things like the different model types, different ensembling strategies, such as different stacking approaches and the related literature on why stacking works, the actual practical stacking approaches that have won major prediction contests, and the light GBM and cat boost papers, just to see how the secret sauce of these models led them to become so popular for tabular datasets.